Okay, class, we're back for Chapter 8, Earth Systems and Resources lecture. To be honest about this one, there is a good amount of content in here, but we're not going to go too deep into the content here. We're basically going to cover topically. So while there is a good amount of information to be covered, we're not going to go very deep into it like we have with some of our other topics. But starting with our case study, the book gives you is about hybrids and hybrid electric vehicles, HEVs. Think like a Toyota Prius, and lithium, and other metals, really. So we know that the benefits of Priuses and other hybrid electric vehicles is that they do reduce fuel consumption, and eventually are designed to reduce our needs on non-renewable resources like fossil fuels. Now the problem is that the things that go into making hybrid electric vehicles also use non-renewable resources, but not the ones we usually think about. Whereas they might use less fossil fuels, they do use more rare metals, things like lithium, neodymium, lanthanum, and that's a bad thing as well because these minerals are just as limited, and if demand leads to more hybrid electric vehicles needing to be produced, it means that we're going to need to mine these minerals more, which means that we're going to need to look for them in new areas. There are areas of the world where these metals are found that have not been previously mined. So we'll have new mining efforts, which is going to lead to physical, destruction of certain environmental areas. And of course, that could always lead to changing environmental impacts. So when we discuss resource use, we are going to talk about it in terms of, like all things, not being a simple, straightforward, cut and dry answer, but something that we do need to weigh all of our options on. So whereas we always have looked at hybrid electric vehicles as being nothing but positive and nothing but good, we do have to look at the downside, which is they are using some non-renewable resources, in this case metals that are mined out of the ground. So when we talk about Earth's resources, and we're starting off talking about a lot of rocks and minerals in this chapter, we have to understand where they came from and understand the fact that what makes them non-renewable is the fact of conservation of matter, that when the planets were created and consolidated from just giant dust clouds, we were given a finite amount of matter on this planet, and that finite amount of matter is not going to change anytime soon. So during all of that collision, while the Earth was still very hot and things were still very molten or liquid, denser particles moved past one another, lighter particles stayed near the top, and we saw that as our planet was forming, we have now some distinct layers that resulted from that. So the layers of Earth you need to know are the core, which is the innermost, and it's mostly made up of nickel and iron. It's solid in the middle with a more liquid outer core around it. The mantle is the layer above the core. It's the middle of that middle layer we're going to look at. That's where you would find the magma. So that is all of the liquid rock that is super hot, moving and circulating in the Earth. And then the top layer is the crust. That's the outermost layer. And obviously, since we live on top of the planet, on top of the outer layer, we live on top of the crust. So here you see in this diagram, we have our solid inner core with a liquid outer core. The mantle, again, is a very large liquid layer with the crust floating on top of it, more or less. The picture up to the side here gives you an idea of scope of how deep the Earth is to the core. So if the core was in Halifax here in Canada, we can see that from the core all the way to the crust extends all the way out to the coast of California, which means we're talking about thousands of miles from the surface all the way down into our core. Now, our top layers that you might have noticed here, our asthenosphere and our lithosphere, those are the important ones because obviously since we live on top and since when we mine things and look for resources, we're only dealing with the top layer. The lithosphere is that outermost layer that we are dealing with when we're talking about resources that we get out of the ground. Alright, now since the Earth is very hot at the center and we know that the magma that makes up the mantle is liquid, we know that what happens when we heat things from the center or heat things from the bottom, we create convection currents where hot things rise and cool things sink, and it creates these convection currents or cycles. Well, those areas where the magma is rising lead to hot spots, where material might reach the lithosphere and eventually potentially the surface. Now, on land, we realize that these areas can be things like volcanoes, but what we don't really notice is that a lot of these areas are under the ocean. So there are a lot of spots where this magma does reach, and many of them happen in the ocean, and since they do happen in the ocean, we don't see them, but they do lead to some interesting circumstances in terms of movement of the things on the crust and on the top of the physical landscape of Earth. Now, since we have things moving, liquid, and we know that we have a thin layer of solid rock on top of it, what that basically means is that if the stuff underneath it is moving, it's going to push this crust out of the way, and that's our theory of plate tectonics. Basically that the Earth itself, the lithosphere, is basically plates that are sitting on top of hot circulating liquid, and since that liquid is constantly in motion, the plates themselves are constantly in motion as well because of those convection currents. Evidence of that is seen in fossil records, fossils of organisms that are found on different continents and in different parts of the world that could have at one point been closer together or connected. Now, in terms of the tectonic plates, you should know that we are on the North American plate, that there are large plates, there are smaller plates, and you can see that at different parts of the world, red here are areas of spreading. These are basically the areas where the magma reaches the surface of the Earth, because that's where the hot areas of the convection currents are rising, and we have these areas called subduction. We'll get to that in a little bit. Basically where plates are converging, because that's where the cooler stuff is basically dropping down towards the center, the denser, colder rock. So one of the consequences of plate movement are areas where magma rises, and since most of them are under the water, we don't notice them, but if they're not under the water, and that rising magma happens to rise in a spot that is not covered by water, that rises on land, we end up with something we call a volcano. And that's basically what we know a volcano to be. And we can see by studying Hawaii that the older volcanoes are the result of locations where plates were millions of years ago, and some of the younger volcanoes areas where they're being currently formed are in different portions, so we know that plates themselves have been moving in this direction, which has led to newer stuff being seen here. So, because of convection currents causing plates to move, plates do a couple of different things. They either diverge, meaning they're moving apart, they're divergent, going away from each other, they're convergent, meaning they're moving towards each other and colliding, or they can be transformed, meaning that they're moving in such a way that allows it to slide past one another. So a divergent plate boundary here is where we're going to see spreading. These are where volcanoes, both on land and underwater, are going to form. A convergent plate boundary is basically when two plates collide, and they're pushing against each other. The rock itself on one of those plates is going to have to get pushed under one of the other plate, and that rock itself will get melted by the magma and the extreme heat underneath that solid plate, and then that rock will basically become part of that convection current again. And a transform boundary is where a plate might be moving not directly into or away from another plate, and as they're moving, they're basically sliding across each other. Now, we see this occur, transform plates, in areas, very similar areas where we have faults, because the rocks aren't spreading, causing magma to rise. Rocks aren't converging, because we can see the areas where they are very few and far apart, where we have areas of subduction, where these plates are hitting each other, and we don't see any of them really on land for them at all. But what we do get are plates that are next to each other that slide past one another and are basically not connected but moving, and those areas where they're not connected but moving across are called faults. They're basically breaks in the rock where that movement is happening. So when we get earthquakes along these transform faults, it's basically some of the rock, whether it's a small amount or a large amount, breaks along a fault and basically sends an energy or a ripple effect up that entire fault line. So these zones are called fault zones, and when we're talking about these earthquakes where this basically large movement of rock is happening where these plates are sliding past each other or these pieces of rock are sliding past each other. The place where that happens, we call it the epicenter. Now, it's not the place in the earth where it happens, it's the place on top of the earth directly above where the rock is breaking or colliding or sliding. Now, you might have heard of the Richter scale before. Richter scale is basically what measures the magnitude of these earthquakes at their epicenters and across the areas that they affect. So the only important thing to know is that the Richter scale is a log scale, so something that is 7, just like the pH scale, is 10 times greater than something that is 6, and so on and so on. So with all of this movement of plates, we can basically not only study the plates themselves, but the rocks that make up these plates, since they're going to be moving as well, since the plates carry physically everything on them. We can study rock movement in terms of the rock cycle. You don't need to know really everything about rocks, but you should know that igneous rock, metamorphic rock, sedimentary rock are the 3 main categories here. And more or less, things will get pushed up to the surface, and things like weathering and erosion, which we'll get to, will basically break them apart, and then they can get compressed or melted back down by magma, and we can track our movement of rock there. More or less, what you need to know for the rocks are that igneous rocks, seen here, are basically just hardened magma. They come directly from magma. Sedimentary rocks are surface rocks, really. These are compressed sediments like sands, muds, things like that, hence the name sediment. And metamorphic rocks are basically rocks that are heated and pressurized so much that they change from one kind to another. So any resulting change in rock due to heat or pressure creates this new kind of rock called metamorphic. And we see here, so things like sandstone or limestone, very common surface rocks, are sedimentary. Granite and basalt are basically the result of cooled magma. And metamorphic rock is basically those rocks succumbing to heat and pressure so much that it changes the original rock into things like marble or quartzite. So when rocks reach the surface, what happens on the surface? We've been talking a lot about the inner parts, but what's happening on the surface that we can observe and control? Well, we see weathering and erosion happen a lot. Weathering is when rocks break down, and this is important because large rocks breaking down to smaller rocks helps set the stage for the making of soil. So physical weathering occurs when you have air, water, or living things like the tree here physically breaking rocks into smaller pieces. Chemical weathering can occur when you have the breakdown by certain chemical compounds that will cause a large rock, so acidification, things like that, can cause rocks to break apart basically by infiltrating a larger rock and cracking it, lowering its structural integrity. Now, erosion is when those broken rock fragments are removed. So that's the difference between weathering and erosion. Weathering is the actual breaking of it, but what we get concerned about is erosion, when you have small rock fragments and things that, small particles that are removed from the area. So when they get moved somewhere, they get deposited somewhere else. They accumulate. So here we see the Badlands, and you can see a lot of the different changes in color here are due to areas that were eroded and those fragments are missing. Hence we have weaker sedimentary rock that had been eroded on the tops, and this harder, different colored rock that's underneath it was less likely to be eroded. And these are the Badlands of South Dakota, very cool rock formations out there that you can see. All the result of weathering and erosion from things like wind, water, the retreating of glaciers thousands and thousands of years ago causes erosion as well. But it is important to think about erosion because we're not just talking about rocks, but we're talking about the things that we usually find on top of rocks, which are important to us studying environmental science, which is soil. Breaking down of rocks is one of the first things that has to happen in order for soil to take hold in an area, is that you need soil to infiltrate organic matter to be able to infiltrate deeper so that plant life can take root physically in a softer material than rock. So weathering and erosion are important parts of the soil and succession process. But we know soil is important because we need it for plant growth. It filters. It's a natural filter for water. And we know that our water, our fresh water, comes from these underwater springs. So the soil itself does help filter out some of the bad stuff naturally that's in there. It does provide habitats. It's a filter for pollutants. we know soil is very important for a variety of reasons. So when soil is made, formation of soil, the factors that go into it, the parent material. So what is it actually forming on top of? What organic material is going to be found there? What rock is it growing on top of? Will provide certain nutrients and provide things that will influence what kind of soil we're going to get. Climate, so warmer climates, wetter climates, dry, again, things like that. Topography, so surface, slope, slope especially, considering movement of water and winds. Organisms that are going to be found in that area, plants and animals that dig or can affect soil formation by adding compounds to it or moving through it. So obviously things like worms are very important for healthier soil because they move through and they aerate the soil. They churn it out and they create areas where air can infiltrate and move through and keep it from drying out. And time. So the amount of time that soil has been spent developing. So soil that's been around for a much longer time is going to be richer in nutrients. Soil that is used more or thinner is going to have less nutrients, which we see what happens on farms and deserted farms is that the soil itself gets leached of its nutrients because they've been all used up, as opposed to areas that where the nutrients aren't demanded so much. So formation of soil, again, we said parent material is important, so the rock material has to get weathered. Some fragments move upwards, creating space. Erosion takes some of that smaller rock away, and eventually organic material. So we already talked about the process of primary succession, leads to mosses and lichens and things like that, which can serve as the organic basis for the process of succession to continue. And as these rocks break, more and more organic material can accumulate and infiltrate the lower levels of that rock, eventually leading to a softer area that tree roots can grow through and grow into. Now, soils will develop layers, and we do need to know these layers. So O, our organic matter, is the top layer. That's where we're going to find the living stuff and the stuff that's breaking down and dying. Topsoil is our zone A, which is going to be organic matter mixed with some underlying mineral material. So if you think about our soil lab we did, what we were really analyzing was topsoil to get a sense of what kind of soil we were dealing with. The deeper you go, you get subsoil, which is the B horizon, which is basically just hard rock, metals, and nutrients. And then the C horizon, which is also subsoil, is the least weathered portion. It's going to be the most similar to the parent material that we would find in that area. The E horizon only occurs in soils that are more acidic. And basically what it does is just capture certain materials in acidic soils. But as long as you know that we have this O, A, B, and C, pretty easy to remember that the top is going to be the most organic material and C is going to be the most rock material with varying degrees in between. So here again are these notes, which you can pause at any time and copy down. Gives you a little bit more detail on that information. The soil triangle should look familiar to you because we did it as part of our soil lab. We already talked about particle size. Know that sand, silt, clay, sand is the biggest, silt is in the middle, and clay is the smallest. The percentages give us an idea of what kind of soil, and what kind of soil we have is very important because certain plants will grow better in certain types of soils. And the different soils, because of their relative sizes, have different permeabilities or porosities. Basically, how quickly things like water or liquids can move through that particular type of soil. So since sand is the biggest, it has the most pockets. Water would move through it the fastest. Since silt is in the middle, silt has smaller particles, smaller air pockets, fewer air pockets that water would take to go through, and clay, being the smallest particles, would have the smallest areas for water to get through, would take the longest for water to move through that. Alright, so that's rock cycle and soil. Now, we were talking about the crust before. We know that the rock material weathers away, but what is that rock material made out of? Well, this is a breakdown of the Earth's crust by element, and these are just by elements and doesn't include any particular compositions of different minerals, specific minerals, compounds, minerals that make up compounds. But you get a sense that oxygen is one of the largest in terms of composition, and you ask yourself why. It's because, well, things like silicon oxide, silicon dioxide, which makes up sand, aluminum oxide, which makes up rust, iron oxide, which makes up rust. These things are all found in the crust of the Earth, just not in their elemental forms and compounded forms. Now, those specific metals themselves are things that we mine, and we do have by this table here certain reserves, meaning at current usage rates and at projected usage rates, how long it's going to take in terms of years to exhaust that. So you see, in terms of iron globally, we're looking at 120 years worth of iron still left, about 40 years just in the United States. And these are estimates. You see this source down here from the U.S. Geological Survey, Mineral Commodity Summaries. These are estimates, and again, usage and things can change that. The fact is that, there are some things that we use, like we mentioned with the hybrid electric vehicles, that we need, that we don't have any reserves for, so we're going to be reliant on importing that. The fact is, you don't see an infinity symbol or any really, really big numbers next to some of these in terms of hundreds or thousands of years, with the exception of iron and aluminum. None of them, more than like our aluminum reserve of 330 years globally, but again, we don't have a lot of aluminum mining in the U.S., so again, I'm going to be relying on imports for that. So how do we get these things out of the ground? Well, we have to mine these reserves, and mining is a very environmentally impactful process, because it does involve destroying the physical landscape to get into the rock and get into the reserve itself, extract the rock, leaving empty space, and then moving on to do something else afterwards. A lot of mines, when they are emptied out, are left in their original state. They are not repurposed. They are not fixed or basically redeveloped to become a part of the natural landscape anymore, which is an issue. Some of the different methods, we have surface mining, so things like strip mining, which is one of the most common ones. It's basically just cutting into the ground in strips of soil and rock to expose that reserve there. We'll look at some images in class of the different kinds of mining and do some activities next week that focus on mining's impact a little bit more. Open pit mining is literally what you think of when you think of like a rock quarry, where you basically have a large open pit and you're just digging out, taking stuff and hauling it to the top. Mountaintop removal is not very common, but it's basically just the removal of chunks of rock, because mountains are made of rock, and if there is a reserve in a mountain, basically just exploding it with dynamite to extract that stuff. Placer mining is the least impactful but also the least productive, which is basically just looking for metals and stones and river sediment, digging up riverbeds, whether old riverbeds or current ones, because the movement of water would have led to cutting out a specific area. It's already doing some of the work for you, and it could be carrying minerals and things from other higher, from earlier in that river's creation. Subsurface mining is basically when we dig below 100 feet, and you could see there are certain minerals that we will subsurface mine for. Again, surface mining is staying close to the Earth's surface, but we could do all of these things deeper into the ground as well. The bigger thing is the effects here to do subsurface mining. And surface mining as well, and you can see that a lot of it does, have impacts on air, water, soil quality. We already talked a lot about biodiversity problems. So we do see that there are definitely some big issues associated with mining, but like going back to our case study, in order to make and do certain things, we do require those resources. So that's our Chapter 8 Earth Systems and Resources lecture. We'll spend not a ton of time on this stuff. We'll go through the basics of it this week, and then make our way over to Chapter 9, which is going to be water resources. Hope you've enjoyed, and enjoy the weekend, and I will see you all next class.